Okay, today we're going to talk about using multiple fixed displacement pumps with an unloader valve in order not to overload an engine. And that is to say, multiple fixed displacement pumps and an unloader valve are used really in order to achieve greater speed when there's no load and yet still be able to hit a maximum system relief in order to move the load. So let's look at what we have here. First off, I have two fixed displacement 100 gallons per minute pumps. I threw an unloading valve in here with a 2000 psi relief spring on it, and I have a system relief with a 4000 psi relief spring on it. I threw in some pressure gauges here, there, all over the place, and I threw in a couple of flow meters to register flow going on in various places. The formula for input horsepower is flow times pressure times a constant divided by efficiency. However, to speed this up, if I take the constant of 0.000583 in imperial and divide that by an 80% efficiency, it works out to 0.0007. So we're going to throw a bunch of numbers at this, and we're just going to try and calculate the amount of input horsepower. That is to say, the horsepower demand on this engine really is. So, if I was to figure out the maximum amount of horsepower draw on this one pump right here, 100 gallons per minute, 4000 psi. So if I was to go flow 100 times the maximum pressure you can see, 4000 psi, times whatever my constant is, divided by efficiency, which I've created a shortcut, I would say that this one pump right here is potentially 280 horsepower. That's what this lovely little phone turns out to. And if I was to do the same thing for the other pump at 100 gallons a minute times 2000 psi times my constant divided by efficiency, simply put, this should be half the flow, half the pressure. Simply put, half the pressure should mean half the horsepower demand. And so really, this one has approximately a horsepower demand of about 140. Well, if my engine only starts with 300, how is it that this pump can pull 140 and this pump can pull 280? So let's look at actually seeing what goes on. So at minimum load, I can just say minimum load, 0 psi, no load situation. This is what goes on for us. I shift this up. Now this 100 gallons per minute is, which was just going through this open center DCB, I get 100 here, 100 here, and I really get 200 here. Yep, no problem. 200. And my actuator's moving. I would see whatever I see for pressure here, I would also see pressure here. So that's not really a very high horsepower demand, 0 psi, even though there's lots of flow. So I'm not even going to bother factoring that in. But let's just throw some resistance on this now. So we'll just throw some load on this. So we throw some load on here, enough to represent 1000 psi. And I should still see 1000 psi here now. And really, I have nothing to open up these valves, so I'm going to do a little calculation. I'm going to just say the combined flow at this, combined flow is 200, and my pressure is 1000. Or 100 gallons from this one, 100 gallons a minute from this one, or 100 gallons a minute from this one. So I get a combined 200 gallons a minute, all moving that actuator. Just like that. So 1000 psi. Let's see what my little formula, trusty formula is here. It's 200 times 1000 psi times 0.0007, a shortcut. Oh. That works out to 140 horsepower, approximately. Oh, well, that's interesting. 140 horsepower, definitely not enough to overload the engine. The engine's capable of 300. So I'm going to add some more to this. I'm going to add a little bit more load to this. And I'll take that up to 1500. And that means I'll take this up to 1500. And that means I'll take this up to 1500. So this was my initial 140 was my initial that we started with. Let's see what it comes out to now. Well, it doesn't seem like much. Let's see, 1500, not 1,000, times 200 gallons per minute, times, 210 horsepower. 210 horsepower. Well, that climbed quite a bit, 140 to 210, and all I added was 500 psi to this thing. So let's throw on a little more load. Let's say that it takes it all the way up to 1900. 1900. 1900. Now let's just see what it says. Still got 200 gallons per minute, all going through that DCV. I'm up to 266 horsepower. Still not overloading this. In fact, out of curiosity, what would happen if I threw on some more load to this and say it went to 2100 psi? Will it hydraulically overload this? If I'm 2100 psi here, then I'm 2100 psi here, and I'm 2100 psi here. The question is, what happened to this flow? If I have enough resistance there to create 2100 psi here, this valve only takes 2000 to open it. So if I have 2100 versus a 2000 psi or pound spring, then I can say that this valve definitely opened. And if I open this valve, then the horsepower demand on that engine drops. 100 gallons a minute times nothing is nothing. There's no horsepower demand on this engine. In fact, the only flow now going to the actuator is from this one. That's the only one still producing flow because this valve hasn't opened up yet. And so actually the horsepower demand is only whatever this particular pump is actually using. And this pump is only 100 times 2100 times 0.0007 shortcut, and now my new horsepower demand 147 horsepower. That is my horsepower demand on my engine. So that's how an unloading valve is. Something had to be sacrificed. When there was no resistance, both pumps were producing all kinds of flow and the actuator was moving quickly. As soon as I threw enough resistance on there, that would have hydraulically overloaded this engine as we seen it climbing, then the fact of the matter is one pump is unloaded and only the other pump is now physically lifting the actuator. In fact, I could keep going up with this particular resistance. I can keep adding more resistance to this, more and more bricks, and I can keep going up and up and up until 3100 times only 100 gallons per minute times 0.0007 is equal to, and now I've got a horsepower demand of 217. In fact, I can keep going up until this relief valve opens, and like we calculated earlier, The maximum horsepower demand just this pump will take is 280 horsepower based off of 100 gallons a minute and the 4,000 psi relief valve in case I physically overload or stall out the cylinder that I cannot physically lift it anymore. Or for example, if I actually dead-ended the cylinder right to the end of its stroke, then this would drop to 0, this drops to 0, and now all of the pump flow has to be going to tank over the relief valve. And that's the maximum horsepower demand we can see. Really, 280 horsepower with one pump, or ironically, if I was to drop this in half to 2,000, 200 gallons a minute is the maximum we'll see on either one of these. It works out to the same 280 horsepower. And this is a stepping stone to the principles and concepts of a constant horsepower system. They take this system and they improve upon it. However, the principle remains the same. The more load you put on it, well, in order not to overload the engine, we have to cut back on flow going to the actuator. So nothing's free and something had to be sacrificed. When there's no load, lots of speed. When there's too much load, slow down the speed. And again, all I know is you gotta have a hook in the water if you expect to catch a fish.